Hi everyone, my name is Hanjun Wu. I'm deeply sorry that due to visa issues, we cannot present this paper at the conference in person. First, thank you all for coming to my presentation. Today I'm going to talk about our work on a compiler framework for fixed topology, non-deterministic, finite automata on SMD platforms. So pattern matching is the core computation of many scientific applications across many domains, such as motive discovery, orthology inference, network intrusion detection. These applications require searching an input text for the occurrence of a large number of textual patterns. Pattern matching can be implemented in non-deterministic finite automata, simply NFA. So as a background, let's see how NFA works for pattern matching problem. The left side shows three patterns defined in regular expression. The first pattern P1 is simply a string of ABC where the first character A may appear one or more times. The second pattern P2 has a character B and C followed by any character that is not E. The third pattern P3 is simply a string of two characters C and D. So our input text to search from is simply ABCD. We can construct an NFA as shown on the right side to search if these patterns appear in the input text. This NFA consists of 9 states. The symbol on the states are transition symbols. Pattern matching is done by traversing the states guided by the traversal symbols and the input text. We have states in double circles indicating a pattern has been matched. So if state 3 is activated, then P1 is found. We have considered 4 transition types. We are going to illustrate them in the example. First, the initial active state is state 0, and the first input symbol is A. We see that A matches the transition symbol between state 0 and state 1, so state 1 is activated. This is called a positive transition. We also see that state 0 remains active. This is due to the wildcard transition represented by the asterisk symbol. A wildcard transition indicates that the transition will take place no matter what the input symbol is. Given state 0 and 1 active with the next input symbol B, we see that state 2 and state 4 will be activated while state 0 remains active. Given these 3 states active with the next input symbol C, we see that state 3, 5, and 7 are further activated while state 0 stays active again. At this point, we know that pattern 1 is matched because the state 3 is activated. The final input is D. We see that there is a negative transition E from state 5 to state 6. Negative transition takes place when the input symbol does not match the transition symbol. In this case, D does not match E, so state 6 is activated. Also, with input D, state 8 is activated on a positive transition. Last, there is an epsilon transition between state 8 and state 9, which means state 9 will be active immediately when state 8 is active. So actually, in this case, all of our 3 patterns is found because all of these 3, 6, and 9 states are activated. With this example, we see that an NFA has 2 major components: the topology of how states are connected and the traversal symbols that guide the traversal. So the motivation of our work is we have found many applications operate on patterns that have the same predefined structure. Motive discovery is one of them. So the left picture shows 2 NFAs with the same topology, and you can see they only differ on transition symbols. The question we ask ourselves are existing NFA implementations on SMD platforms the best fits for fixed topology NFAs? So most of the existing implementations, they store topology of states and transition symbols both in memory. This leads to a memory-centric NFA implementation. Actually, we found out that these are not the best for fixed topology NFAs because memory becomes a bottleneck soon. Based on our 2 observations, we think that there is a better solution. The first one is we can embed topology into computational kernels since all the topologies are the same. The second is we can organize transition symbols for better memory access patterns for all of these NFAs. So the goal of this paper is we have proposed an SMD NFA, which is a fixed topology NFA engine on SMD platforms. we want to achieve the following. First, we want to embed the NFA topology within the parallel kernel. Second, we want to deploy our design on various SMD platforms, such as NVIDIA GPUs, Intel Xeon Phis, and Intel Skylake processors. Third, we want to achieve full utilization of SMD lanes on these platforms. Fourth, we want to achieve regular memory accesses in kernels. Last, we want to automate the deployment of our design on these architectures. To this end, we implemented our SMD NFA compiler toolchain. So at the core of our toolchain is the design of our SMD NFA engine. It consists of several design modules. The topology-driven kernels embed the NFA topology into the code. Memory layout module reorganize the transition symbols for regular memory accesses during runtime. And we target several SMD platforms, including NVIDIA GPU, the Intel Xeon Phis, and Intel Skylake CPUs. However, manually generating the kernel and the memory layout is tedious and error-prone for different topology. So we have engineered a compiler that takes NFA description files as inputs and generates the design automatically. Our compiler also performs several device-specific and device-agnostic optimizations. For the rest of my presentation, I'm going to focus on the SMD NFA design part, which is highlighted in red block. You can refer to the paper on how the compiler is engineered. This is the high-level pseudocode of our traversal design. To begin with, we need some data structures that hold the state's status on being active or inactive. So we have three state vectors in our design. I'm going to talk about their layout details in the next slide. So now we can see that the current state vector indicates the status of states before processing a symbol, and the future state vector indicates the status after processing input symbol. The persistent state vector indicates those states which should remain active once activated. For example, the beginning state 0 and accepting states, they should remain active once they are activated. So we see that on the left side is the fixed topology NFA traversal pseudocode. For each while loop iteration, we first make persistent states active at line 3. We then have each SMD lane read an input symbol at line 4. Line 5 actually performs the fixed topology traversal, and line 6 updates the future state vector for next iteration. The while loop will stop when input stream is empty. So the code looks serial, but in fact, it is executed by every SMD lane. And at line 5, the traversal constantly updates the current state vectors and future state vectors. The layout of the state vectors is actually crucial for the performance. So now let's talk about the layout of the state vectors. We have a compact design for state vectors so that they can be put into fast memory, such as shared memory on NVIDIA GPUs, or they can fit into L2 cache on Intel processors. We use bit array for all state vectors, where bit 1 indicates a state is active. As the top left picture shows, since the two NFAs share the same topology, we give their states the same identifiers. States are labeled from 0 to 6 the same way for both NFAs. Here we just have two NFAs, but with a real dataset, we may have hundreds of NFAs. So we group states with the same ID from all the NFAs together, as shown in this bottom picture. We see that bits representing status of the 0 state across all NFAs are contiguously organized in memory, and we do the same for the other states until the end of the state. So with this design, each SMD lane takes care of 32 bits. We call it batch size. Thus, each SMD lane handles 32 NFAs concurrently. With this design, updating state vectors becomes bitwise operations, and it is very efficient. Now let us look at our fixed topology traversal. So on the right side, we have NFA. This NFA has all 4 types of transitions we considered. The transition symbols are for illustration purpose only. Actually, every NFA has its own set of transition symbols, and our engine processes all the states sequentially as indicated in the left side pseudocode. Transitions are embedded in the code based on the order of the source state. So first we embedded the transition starting from source state 0, then we embedded the transition started from source state 1. You see that this is actually a serial code. However, the execution of the if loop is parallelized on vector units. So first, for source state 0, we see that there are two transitions, one to state 1 and one to state 3. So, more detail. For the transition to state 1, there are two functions evolved. The check function basically checks the input symbol against the transition symbol, which is A or B here. So we use A or B for illustration purpose. In fact, the transition symbols are different for every NFA, and they are fetched from memory. Since each SMD lane handles 32 NFAs, the check function will generate a mask of 32 bits. Corresponding bit will be set to 1 if the input symbol matches the transition symbol of the related NFA. The mask is then used in the second function, positive transition, which updates the state vectors of 32 NFAs. Due to our state vector layout, the memory access here is regular and contiguous. For the transition to state 3, we see there is also a positive transition embedded. Next, for source state 1, we see that there are two destination states 2 and 3. For transition to state 2, it is simply a negative transition. However, for transition to state 3, there are two transitions embedded. One is a wildcard transition, one is an epsilon transition. So as I said before, totally we have 4 types of transitions. Here I show how negative transition is implemented. So since negative transition is only taken when input symbol does not match the transition symbol, here we just simply nag the mask, nag all the bits of the mask, and perform a binary AND with the current status vector, then commit the result to the future status vector. The other 3 transition types are implemented in a similar way. So this is basically our design, and all of these embedding of topology is done by our compiler. Also, the transition symbols are also reorganized by our compiler. But due to the time limit, I'm not going to talk about the reorganization of transition symbols here. You can refer to the paper for more details. So this is our experimental setup. So we have conducted experiments on 6 platforms. Basically, we have 6 SMD devices. 3 of them are NVIDIA GPUs, and 3 of them are Intel processors with 512-bit vector units. We tested these devices of different architectures, with as old GPU as Kepler architecture and as new as Pascal architecture. For Intel processors, we have as old as Knights Corner coprocessor and as new as Intel Skylake processor. So the dataset we considered has a variety of characteristics. We have 6 input datasets, and they have different number of states, and they have different combination of the 4 types of transitions. We derive our baseline from Infant, which is a famous memory-centric NFA engine on GPU. We extended it to make it work on Intel processors, and we have verified that our modification is faster than the original implementation. So here is the result on GPU devices. X-axis actually is the input dataset. Y-axis is the throughput in kilobytes per second. The solid bars indicate the results of our SMD NFA design, and the stratified bars indicate the baseline implementation. Bars of the same color means experiments are performed on the same GPU devices. We see that our SMD NFA outperform baseline on 4 of the dataset, and namely HD small Fermi, LD small, and LD large. And on average, we have achieved On average, across 7 datasets, we have achieved 4 times speedup on Kepler architecture, 1.5 speedup on Maxwell architecture, and 4.3 speedup on passive architecture. So in fact, we can see that our design benefits more on old architecture, where memory bottleneck is more of a problem. So this slide shows the results on Intel platforms. We found our SMD NFA design is consistently better than the baseline implementations across all datasets. On average, it is 10.7 speeds up on Intel Skylake processor, and 11 times speed up on the Xeon Phi processor, and 46 times on Xeon Phi Core processor. Again, we find our design benefits more on older Intel architectures, where memory bottleneck is more of a problem. So there are more detailed of analysis on each data. There are more detailed of analysis on each dataset in the paper, and you can refer to the paper for details. Also, we have performed various memory consumption analysis and power consumption analysis, and our result actually shows that our design is memory efficient and is also power efficient. So, to conclude my presentation today, we have proposed a NFA processing engine called SMD NFA, which is for fixed topology NFA traversals on SMD platforms. And compared with traditional memory-centric design, we achieve better performance with most datasets on GPU, and we achieve significant speedups on Intel processors with vector units. Currently, we are doing our future work. We consider our future work. For example, we are investigating our design on FPGAs. So that's all. And thank you all for coming to my presentation today. And again, I'm deeply sorry for I cannot make it to present at the conference. And feel free to contact us for presentation slides and the YouTube link. Below is our contact method. Thank you. Bye-bye.